I do a whole lot of research that all kind of falls under the umbrella of constraining the Drake equation, even though it's all in the field of exoplanets, but it's kind of almost unrelated fields. I study early planet formation. I study, hot Jupiter atmosphere. I also run simulations of what we can do with the next generation of extremely large telescopes. And so, yeah, that's what I'm here to talk to you about today. So I'm going to do a fun little introduction about, how long have people been thinking about the search for life. Then I'm going to get into some science and say, okay, well, using this survey that I'm the PI of, how can we sort of determine the origins of planets in the universe? Then I'll have a question break. Then I'll get into modern day exoplanet spectroscopy and talk about, what I do with hot Jupiters right now. And then we'll have another question break. And then we'll talk about the future of what we're going to be able to do with extremely large telescopes. So when people think about, SETI or, the search for any kind of life out there in the universe, they usually think about, the organization SETI, and we think of Jill Tarter listening to, radio wave from the universe to see if there's anything intelligent out there. But people have actually been thinking about this problem for an extremely long time. I'm going to talk about some religion and philosophy that have had ideas going back 2,500 years ago. So there are Buddhist texts which indicate that people are thinking about, life that is intelligent but not Earth-like. Hello, cat. The Greek philosopher Metrodorus of Chios said that it would be super, super weird if the Earth was the only inhabited planet out there in all of space and time. The Quran actually says that there are perhaps creatures and intelligent life in the heavens in addition to the Earth. And the Hindu text, the Bhagavata Purana, says that not necessarily that there may be other intelligent life out there, but that there are countless universes. And so each of these universes could potentially, host an Earth like our own. So I also want to talk about science fiction with respect to the search for life. In the ancient world, we had Lucian of Samosata publishes a discussion of speaking with extraterrestrial beings. In Japan, we have this narrative called The Tale of the Bamboo Cutter, which is the story of a woman from the moon who has family from elsewhere in the solar system. And then you might be familiar with 1001 Nights, which also includes stories about travels in the space from the other world. And so basically in science fiction in the ancient world is kind of it's starting to think about what if we're not the only people out there. If we start to kind of skip forward to the Enlightenment, we have Margaret Cavendish's work in 1666. Voltaire's Micromegas is really actually very far ahead of its time in suggesting not only are there other worlds that are inhabited, but these other worlds might be more technologically advanced than people on Earth. We also have Gulliver's Travels, which describes alien civilization. And so in the Enlightenment, people are kind of asking, what might aliens be like if they do exist? In the 19th and 20th century, we have kind of the very beginnings of science fiction. We have people speculating on what alien civilization might be like. Jack London writes a story called The Red One, which is about a message that is sent by aliens to a civilization on Earth. The civilization had advanced enough to know how to interpret it. And so this is kind of asking the question, how would humanity interact with other life? And then I also, of course, I have to talk about the Golden Age. So, we have Asimov, Arthur C. Clarke, Ray Bradbury, people like that. These people are exploring the themes of alien encounters from kind of an atomic age, very like a fearful perspective, kind of. So Golden Age science fiction has a lot of aliens as being a threat to humanity, or they're like you have like Heinlein's A Stranger from a Strange Land. That's a story of, a man from Mars who's coming to save the world. But as you move into modern science fiction, you have like N.K. Jemisin, Leo Sacheen, Margaret Atwood, perhaps you've seen The Expanse, even Carl Sagan wrote science fiction. And these people are integrating the themes of alien encounters into more of the literary genre, and they're starting to really sort of see aliens as like a reflection of society and not just as a black and white threat or savior. So that's my nice little history of, the search for life. So really this kind of all leads up to the big question, which is, are we alone in the universe? And in 1961, Frank Drake had developed a mathematical expression, hello cat, that says basically, how many people are out there that we could actually talk to today? And so that has to do with, how many stars there are, how many of those stars have planets, how many of those planets are habitable, how many of those habitable worlds are inhabited, how many of those inhabited worlds actually have intelligent species on them, how many of these intelligent species are technological. And finally, we have this unknowable constant stuck there at the end that says, okay, how long does a technologically capable and communicating civilization actually last? Well, that one is totally unknowable, but we can focus on some of these terms that are earlier in the equation. We can focus on, how many planets there are per star. We can say, okay, using spectrographs today, could this planet be potentially habitable or not? And we can also say in the future, in 10 years, when we have extremely large telescope, we may be able to put some constraints on not just is a planet habitable, but is it inhabited? So first I'm going to talk about the past and when did planet formation begin in the universe? So I developed this project back when I was a grad student. It's called the Search for Exoplanets Around Metal Poor Stars with TESS or seamstress. And seamstress's big question is, when did stars begin to have planets? And this kind of breaks up into several smaller questions, which is really, what's the minimum metallicity for a planet to form? Metallicity very roughly tracks with age. What kind of planetary systems were the first systems to form? And could an ancient star potentially support life? So where do we begin with a big question like this? Well, I would say that the first thing that you need is just a whole hell of a lot of data points. So we start with TESS. We cross-map TESS with large surveys like Gaia, SkyMapper, Lamos, Galah, Apogee. I'm going to focus on SkyMapper and Gaia for now. And I do want to emphasize that there is a little bit of data out there already, but really not much. This is about 30 stars that are confirmed to have planets below metallicity of -0.5. So let's start with seamstress SkyMapper. SkyMapper has 250 million stars in it. My colleague Ani Chidi ran all those stars through a neural net, which turned the photometric colors into metallicities and log G values. So this gave us 75,000 stars, which were metal poor, and they were dwarf stars, meaning we could actually see a transit if it happened. 28,000 of those stars had test matches, 3,200 had threshold crossing events, or basically promising exoplanet signals, and 50 of those turned out to be actual planet candidates, of which 28 still remain in our sample. So this is just a nice visualization of the size and the metallicity and the period of planet that we have, planet candidates, which we've discovered. So you can see that a majority of these planets are hot. They have, these planet candidates are hot. They have periods below 10 days. One of them is a little bit longer period. They're kind of clustered between -0.6 and -0.8. We do have a few that are just below the literature limit, which is -0.89. Some of them have had a little bit higher metallicities once we've gone back and checked them with actual spectroscopic metallicities. The stars that, or the planet candidates that exist below the literature limit are mini Neptune size. They are queued for spectroscopic metallicities. I think we got one metallicity for one of these stars a while ago, and then the other two are still a little bit unknown. And then we also are doing photometric follow-up through TFOP. And then just you might be asking yourself, well, how good are these photometric metallicities? And so here's just a nice demonstration of the comparison of photometric versus spectroscopic metallicities. We have the photometric on the x-axis and the spectroscopic on the y-axis. And you can see that everything's pretty well contained within 0.3 dex. Not sure what happened here. But largely our sample is, very pretty well calibrated. So what are we actually going to be able to do with this information? I would say that once we finish the Seamstress Sky Mapper sample, because this covers the entire Southern Hemisphere to a certain magnitude range, we're actually going to be able to place meaningful constraints on planet formation, basically saying, okay, what is happening at low metallicities, with the caveat that we can't detect Earth-like planets or Earth mass planets or Earth radius planets essentially around metal poor stars, just due to the limits of tests. And so basically, we kind of divided up our expectations into a low yield, which means that planet formation, core accretion, pebble accretion model are probably working just the way we expect them to. What's most likely is that we get, 3 to 8 planets out of this sample, and we say, okay, well, maybe there's some exceptions to models depending on where they fall in metallicity space. And this might point to like chemical abundance dependence. We know that metal poor stars are usually particularly alpha enriched. Maybe this alpha enrichment has something to do with planet formation, where the alpha elements take the place of iron in your planet formation equation. And then if we actually get a whole lot of planets out of this sample, then that'll mean that we need to perhaps make some changes to core accretion and pebble accretion models. We also looked at planets in the halo. So the halo is this, big spherical, low density area of stars which surrounds the Milky Way. It has 2 components. The inner component is the remnant of the large past merger Gaia Enceladus. The outer component is the remnants of dark matter dominated stellar systems. Both of these have very, very low average metallicities. So you can actually use kinematics as a proxy for metallicity in this kind of scenario. Let's see, yeah, so we started with Gaia, and we had 1 million halo stars. Most of those were giant, most of them were too faint for tests. So we ended up with 4,000 test matches, 700 threshold crossing events. And once we went through those 700 TCEs, we actually got no planet candidates whatsoever out of the entire sample, which is saying something. So basically, if you look at the NASA Exoplanet Archive, then NEA says that, sometime after metallicity of -0.1, you have planet formation turning on in the universe. Seamstress Sky Mapper is saying basically the same thing. And then Seamstress Gaia is saying that, well, you don't have planets as detectable planets in the halo. So given the age of, the average age of the halo, we can say that, planet formation, at least in the regime we can detect, didn't really turn on until 2 to 4 billion years after the Big Bang. So to conclude this section, we're constraining planet formation rates in the early universe. And ultimately, this is going to tell us how long life is, how long life has had to exist, and where in the galaxy you will find it, and where in the galaxy you won't find it. So I'll break for questions.
Feel free to raise your hand or post questions in chat if you have any.
Yeah, Joe, please monitor the chat. I cannot see it.
Yeah, no problem. All right. Doesn't look like we have any for this section right now.
Okay. I will move on to the next section. So now I want to talk about how we can better constrain planetary atmospheres with the technology that we have available today. So if you ask a theorist, how do we tell if a planet is Earth-like? They're going to say something like, well, you look at the biosignatures of that atmosphere, and then if there's, a biosignature or there's a biosignature pair, then you can say this was probably produced by an organic, like, a life source, similar to what happened on Earth. But if you ask an observer this question, they're going to say, okay, well, you have to detect anything first. And let me tell you that detecting an atmosphere on any kind of planet is a non-trivial exercise. So the way that we solve this problem is with high resolution cross correlation spectroscopy. Just to break that down, spectroscopy being the study of emitted or reflected light from an exoplanet. Cross correlation is a statistical comparison method, and high resolution just means that we have a whole heck of a lot of data points in our spectrum. So we use HRCCS. My group actually specializes in 3D atmospheric models. I don't have a lot of time to talk about that right now, but You can definitely ask me later about the global circulation models, the GCMs that we run, and the result that we get out of them. And then one kind of new concept I want to introduce is multi-epoch observations of the kind of planet we study, which is hot Jupiters. Since hot Jupiters are relatively easy to characterize with respect to, sub-Neptunes and super Earths and things like that. So the problem that we have at hand is really that when you study a hot Jupiter at just the day side, or if you study it just in transit, it doesn't really capture the 3D property of the entire planet. So the solution is to study the planet at not just the day side, not just at the night side, but at 5 different epochs around the orbit, with the caveat that the less of the day side you see, the lower your signal noise get, and trickier your models become. So the key idea here is that the planet spectrum is going to change with phase. So if you look at this day side spectrum, you'll see that it's emitting. Emitting just means that, something is hot. But if you look at these 2 symmetrical phases that are kind of near quadrature, we'll call these the day side quadratures, you'll see that you get spectra that are not only different from the day side, but also different from each other, even though they're at symmetrical phases. So why is that? It has to do with the actual nature of the hot Jupiter itself. So hot Jupiters are fairly well known to have an equatorial jet, which goes eastwards around the planet. This is due to I'm not an expert in meteorology, but it has to do with the fact that, hurricanes go one direction in the north and they go one direction in the south. And when they meet at the equator, they produce this eastward jet. And so the jet is about 2 kilometers per second. And it's so strong that it actually takes the hot part of the planet, the hot spot, and it advects it toward the east. It just pushes it away from the substellar point. And so when you look at this face of the planet is actually a lot hotter than this face of the planet, because you're seeing more hot spot here than you are over here. And so that's why you will get these different spectra, even though these phases are symmetrical about transit. And you can also see that you'll get the same result for the night side quadratures. So essentially, we collect multi-epoch spectra of the planet. We do the whole cross correlation of the extracted data with the model. This project was allocated 1 night of time of Gemini, IGRIN, and also 1 night of Keckner spec for the semester. So we have obtained about half of the spectra that we expect to be able to publish for this semester. And I'm very excited about the Keck data that we just got of the night side of WASP 33. It's getting reduced this week. I don't have results quite yet, but I'm very excited about it. It could potentially be the first detection ever made of the night side at high resolution of a hot Jupiter, or really any planet. But we also want to think about other instruments besides IGRINs and NIRSpec. So one thing I've been doing is I've been working on a simulation of a new instrument called WineRed. WineRed is slated to go on Magellan in fingers crossed next year. WineRed has twice the throughput of IGRINs, which is really exciting. It has 2 higher res bands at 70,000 and 1 less high res band at 28,000. The lower res band covers both the Y and the J. The high res band covered the Y or the J. So preliminary analysis suggests that WineRed will actually be able to detect the the night side of even a cooler, or the cooler night side, not just the warmer night side, but the cooler one of the hot Jupiter WASP 76. That's kind of our test scenario. These spectra were generated by Haley Belts for an upcoming paper on ultra hot Jupiter magnetic fields. I think that's actually on arXiv already. Very cool. Go check it out. One thing that I do want to mention is that the day side is about 1 magnitude brighter than the night side. So that is kind of the level of detail that we're dealing with here. And this plot has a lot of information on it, so I will go through it kind of slowly. Basically, we found that when you compare the wideband and the J-band and the wideband, when you're trying to calculate the planetary signal and noises which is retrieved through your analysis, or your detection significant, which is retrieved through your analysis, for these 5 phases. Sorry, this is a lot of information jammed into one plot. We see that you get the most planetary signal to noise, or you get the highest detection significance when you use the J band. So you'll get, you know, adequate performance with the Y band. But I was surprised to see that you actually will not really get anything significant out of the wideband. And I think this is because the resolution is just a little bit too low for this kind of science to actually happen, because in the method that we use, in the method that many people use, PCA or air mass detrending, you're basically relying on the planet's signal to shift across wavelength elements. And so if you have a low resolution, it takes a long time for the line of an exoplanet to move from one pixel to the next. And so I think that's what's happening with the wideband and why we're not getting super great results out of it. I also want to point out that this 100 and this 70 refers to the signal to noise of the star per exposure. And so we found that when we take twice as many exposures at 1/√2 of the signal to noise, you get significantly better results when you take more exposures with less signal to noise. So keep an eye out for this paper. I'm hoping and praying it will be submitted by the end of the year, but I'm also moving, so it could be next year. And finally, I just want to, let's see. I want to talk about, I think I have time to go through this section. I want to talk about how imperfect detectors and reduction pipelines can affect the quality of the detection significance that you usually get out of your standard air mass detrending or your PCA method of detecting an atmosphere. And I want to talk about the solution that I come up with these problems using my background in stellar spectroscopy, with the caveat that, when should we use this method? How do we implement them? It's all on GitHub. I'll talk about it more. So once we have the models, once we have the spectra are reduced from raw images to usable flux wavelength arrays. This kind of the bottleneck of this process is that you have to remove, when you're observing from the ground, you have to remove tellurics, which are just lines from the Earth's atmosphere. You have to remove the stellar line, and then you do your cross correlation. But telluric and stellar line removal is really the bottleneck of this process. So the key concept here is that an exoplanet spectrum, it has 3 components. You have the star. The star's lines do not change in position. They do not change in depth. This is not an entirely true statement. There are star spots. There are flares, things going on with the star that are very hard to separate from planetary activity when you're looking with transit. But for now, we're going to pretend that the star doesn't change. The telluric change in depth, but they don't change in position. Really depends on the level of atmosphere and the turbulence of Earth's atmosphere that you're looking through when you're making this kind of observation. And the exoplanet spectrum will change in position, and it will also change a small extent in depth, because you may have your spectrum going from like an emission spectrum to an absorption spectrum or something like that over the course of your observation. So there's 2 key points of this paper that I submitted in August. The first thing is that your spectra need to be perfectly normalized or flat, perfectly normalized between 0 and 1. And so I have a tool to do this called SPORK. And the second thing is that systemic noise needs to be eliminated to the greatest extent possible when you are removing telluric lines. So this is a little bit challenging to see, but this is about a 0.5 deviation from the continuum, which is this line at 1. 1 is where we want everything to be perfectly normalized to. But you can see in this spectrum, which was actually published, that there's a 5% deviation at this particular part of the spectrum. And so you might say, okay, well, that's not a huge deal. But if you think about how small the exoplanet spectrum is, the exoplanet spectrum is 1 or 0.1% of the star spectrum. if you're dealing with, 0.1% of a spectrum and you have a 5% deviation, that can actually seriously mess up your analysis. So SPORK, which is the red line, SPORK has been kind of fine-tuned for absorption spectra, so that it's very good at finding where the continuum of the spectrum is. It knows when to ignore large scale features. It really just does this with sigma clipping. There's no machine learning or anything involved with SPORK. And so you can just fit SPORK to a spectrum which has some deviations in it and divide it out, and then you're left with a perfectly flat spectrum. You can also use SPORK after you've removed tellurics. So this is this is, again, this is published data, this telluric removed spectrum here, but this gets cross-correlated against this particular model right here. And so if you want to cross-correlate against this model, which has been normalized, well, your spectra have to be perfectly normalized as well, because these deviations here, which you can see with the red, are not quite, they're just inhibiting you from getting the best results out of your cross correlation. So we can fiddle with the parameters in SPORK actually, and we can set the sigma clipping and the notch spacing to be a little bit different. And then we can just divide out the SPORK fit, and then we're left with a perfectly flat telluric removed spectrum, which we can cross correlate really nicely against our model. So when you have really messy spectra, when everything's deviating in a different way from the continuum, I would use SPORK before you even put it through telluric removal. Telluric removal being air mass detrending or PCA or whatever you have. If you have time series spectra and they're all deviating from the continuum in the same way such that it shows up in your telluric spectra, I would recommend using SPORK after telluric removal. But you should test all scenarios, really. It doesn't matter what kind of telluric removal process you use with SPORK. And then I also want to talk about iterative smoothing, which is just saying that if you apply a very, very slight degree of smoothing to your median spectrum when you use air mass detrending, this will this can really increase the amount of signal that you are retrieving, just because you're getting rid of systemic noise in the median spectrum. So if you have like one, it won't be just one, it'll be a lot. If you have one bad pixel in the detector, which is constantly throwing up some, like just a slightly higher or lower value than it's supposed to, iterative smoothing will get rid of the effect of those bad pixels. So you can see here what we did is we just fit, the red line is the smooth median spectrum, the smoothing factor of 0.12, and you can see how good of a fit that is. We're not doing any dramatic, like super overfitting here. The blue line is an overfit. You can see it's not quite fitting all the features. And so the way the iterative smoothing works is you just run your whole telluric removal and your analysis code 1,000 times. This is why you have to do it with air mass detrending, because air mass detrending is fast, unlike PCA. So you just run it for all of your smoothing values, and you can see that without smoothing at all, you have a detection significance of about 9. This was after SPORK was applied. But when you apply some degree of smoothing, you'll increase in detection significance until you reach some kind of plateau. These regions out here are just to demonstrate that this is too much smoothing. You'll get really chaotic results out here. But somewhere in the regime of like 1.1, 0.2, you'll get this nice plateau where you can just choose a value from the region of stability, and you can just you can apply this degree of smoothing to your median spectrum when you do air mass detrending, and you can really get at least like a 1 sigma boost in detection significance. So here's some results. This is HD209458b, one of our favorite canonical hot Jupiters. And you can see that this published detection significance was 5.78 in Belts et al. 2021. And then we applied SPORK and we applied iterative smoothing, and we increased this signal by almost 4 sigma, which is just really a huge amount, without affecting like the shape of the smear of significance. We also tested this on HD179949b, a less popular, less cool hot Jupiter. And we managed to go from about 4 sigma to about 6 sigma here. And the reason those are so different is because this scenario used a 3D GCM model to fit the data, and this was a 1D model. You can also do this with with just regular SNR tests. So this was done with sort of a specialized method just for that data set. And this was done with a very run-of-the-mill SNR test and t-test. And so you can see that we got some significant increase with the SNR test. Worst case, you might not see any kind of significance with the t-test or whatever you use. For this planet, we got a SNR increase of 1 and a significant increase of about 1. So this was all done with CRI-RES data. This works really well with CRI-RES because CRI-RES has some known and fixable issues, which are what I'm presenting in this paper. This works well with iShell data. iShell has some flat fielding issues, and sometimes you might have some messy spectra coming out of it. So we tested this on combined iShell and Aries data from a paper that one of my friends wrote. And so once we applied SPORK for both before and after, we recovered, a small increase in significance with the traditional t-test method. And we also tested this on IGRINS data. So IGRINS is a really, really good instrument, but it's not a stabilized instrument. And so you can have deviations in your spectra over time. Let's see. Okay, this is an older slide. We actually have tested this. We made further tests of IGRINS data, and we did see that some improvement can be made with SPORK. So this paper is now on arXiv. All of our code is on the GitHub of our group's undergraduate research assistant. And so I want to conclude this section and say that ultimately we're enabling the clearest and the most coherent pictures of exoplanets yet taken by using multi-epoch observations and by improving the way that we analyze data. And so ultimately, this is going to tell us with today's technology, not just do we have a planet, what's it made of, but like could a planet, like potentially a bright mini Neptune or bright super Earth, could this planet host life? I'll break for questions again.
Thank you so much, Kaitlin. This is really interesting stuff. I did have one, and anyone else is free to raise your hand or post them in chat. But when you're using SPORK, do you have to make modifications if you're looking at a different type of planet? Like, is it only working for hot Jupiters right now? If a planet had a different dominant molecule in the atmosphere, would it be able to take that into account?
Yeah, so SPORK is super, super flexible. I use it to do trend light curves. I use it to, because you can set the sigma clipping, which is basically, ignoring some sigma deviation away from the mean. You can use it for pretty much anything. I mean, stellar spectra are absorption spectra, which is what it's optimized for. So for any kind of exoplanet spectrum that you expect to see, whether it's emission or absorption, SPORK will deal with the stellar spectrum and make sure that the stellar spectrum is as clean as possible before you go in and you try to retrieve your exoplanet spectrum from it. And it can be used for light curves. It can be used for pretty much any data set that has some kind of trend in it. You can fiddle with the parameters and get it to fit out whatever trend you have. It's super flexible.
That's awesome. Thank you so much. And we have a question in chat. It says, even if we are able to readily characterize exoplanet atmospheres, which biosignatures give you a high confidence that they are caused by biological processes and not physical planetary processes?
That is a great question, and I'm going to talk about it in my section on ELTs, which is next. I do have like a nice big list of biosignatures, including phosphine. I have lots of phosphine opinions, and also biosignature pairs as well as anti-biosignatures. So I will talk about that in a few minutes.
Awesome. Does anyone else have any other questions about this past section? All right, I'm not seeing any, so I'll leave it back to you, Kaitlin.
Great. Okay, let's talk about ELTs. So this is kind of research that I have been preparing for by writing up this simulator for the wine red spectrograph. And in kind of my next postdoc, or the next year or so, I'm going to be actively working on simulating like EELT, TMT, GMT, wherever I get put, that's the telescope I'll be working on. So let's talk about the European Extremely Large Telescope, EELT. This is going to have a spectrograph called METIS. METIS goes between 3 and 5 microns, resolution of 100,000. It's assisted by a coronagraph, which is fairly unique to this telescope, and adaptive optics. University of Michigan is the only US EELT collaborator. So if you want to work with the largest ELT, which is coming online, come to Michigan. TMT has a spectrograph called MODIS, which goes between about 1 and 2.4 micron, same resolution, has adaptive optics. US partners are Caltech, the UCs, and ARA. The Giant Magellan Telescope has a spectrograph called GMT NIRS. And this has actually a really wide wide coverage. It has resolution of 65,000 in the JHK band, 85,000 in the LM band, also has adaptive optics, lots of US partners. So what can we do with this, with these 3 ELTs in the hot and the ultra hot Jupiter regime? So one goal that we've had for ultra hot Jupiters is to figure out where they form, because we don't know if they form far out and then migrate in. Do they form close in and then they just stay close in? But if we knew what they were made of, we would be able to tell where they came from, because different elements sort of condense at different distances from the star when they're being formed. And so one thing we'll be able to do with ELTs is to characterize not just like the atmospheric circulation and the planetary rotation rate, but also the actual abundances of the atmosphere. We'll be able to do this much more reliably. I think Mike Lyons just published a paper on WASP 77 where he had just like 0.3 seeing or something ridiculous like that. He got some really, really good data and was able to do a retrieval and get some abundances for one hot Jupiter. But that's not really commonly practiced yet, because we just don't have the quality of data yet available to do this kind of science. But with ELTs, when you significantly boost your signal to noise, you significantly boost the throughput of the spectrograph and the resolution, we will be able to determine abundances for hot and ultra hot Jupiters and constrain their formation scenarios. In the super Earth and mini Neptune regime, we hope to do some of the same things, like characterize, atmospheric circulation, find out how fast these planets are rotating. This is an interesting regime because there are going to be inhomogeneities, which are going to correspond to like dynamic atmospheres, just like the Earth has a dynamic atmosphere. It's not just like a blanket cloudy on the night side and, not cloudy on the day side like a hot Jupiter, but, we have variable clouds and a rotation rate that's not tidally locked and stuff like that. So we really want to actually observe inhomogeneities in mini Neptune and super Earth atmospheres. And finally, we also want to measure mass loss rates. So this can tell us about the kind of the valley between super Earth and mini Neptunes. We think that super Earth may start with some kind of primary atmosphere made of light elements like hydrogen and helium, and then maybe they lose that atmosphere and they gain another atmosphere, a secondary one, through like magma outgassing and stuff like that. And so if we can really get better at measuring mass loss rates from like mini Neptunes, we can start to pin down the time scale of that kind of process. And finally, I'm going to talk about the Earth-like regime. This is almost completely unexplored right now. It's really not well characterized. There was a 2015 paper by Ignace Snellen that said, if you take a whole entire night to observe an Earth-like planet, then maybe you'll get like an albedo measurement or something like that. So this is actually going to be super, super difficult, because the contrast of a hot Jupiter is like 10 to the -3. The contrast of an Earth-like planet is like 10 to the -8. That is a huge, huge leap in contrast. And it may take something beyond a 40-meter telescope with a brand spanking new spectrograph to actually measure the abundances of an Earth-like planet atmosphere. So that's something that's really very unexplored. And I personally am going to be working on this problem in the next couple of years to not only, you know, improve on what kind of simulations we have today, but also to really start to grasp what we can do with ELTs. Could we measure the albedo of an Earth-like planet around a G dwarf? What if it's a white dwarf? What if it's an M dwarf? This regime totally not well characterized at all, and that's what I'll be working on the next few years. So let's say that we can observe the atmospheric abundances of an Earth. What are we going to be looking for? Biosignatures are basically gases which, when they're present in an atmosphere, they indicate they have biological sources responsible for creating them. What's stronger than a biosignature, which is more convincing, is a biosignature pair, which is a pair of gases. When they're both present in the atmosphere, they indicate that there's some kind of chemical disequilibrium, which is being triggered by a biological process. So if you see, you know, two of these particular gases together in an atmosphere, you might be able to say, okay, something that is Earth-like, something that we have studied before, could potentially be responsible for creating this biosignature pair. Although, you know, it could always be some kind of unknown geological process. That's what the big debate's going to be all about in 10, 20 years when we start looking for biosignatures and when we start finding them. It's just going to be years of debate of people saying, well, what if this process caused it? What if this process caused it? And of course, there's also anti-biosignatures, which are gases which are inhospitable to life, with the caveat that life as we know it. So there's a whole lot of biosignatures. Phosphine was in the news lately in Venus's atmosphere. Feel free to ask me my opinions about that. As a spectroscopist, I have many opinions. Biosignature pairs are O2 and methane, and then methane and CO2. And the big anti-biosignature is really carbon monoxide. So this is a really nice paper that came out last year that says, okay, what if you have an Earth that is in transmission around a white dwarf? So this is spectra for if the planet is really far from the white dwarf, and this is spectra for if the planet is like near the Roche limit of the star. But basically, these are O2 and CO2 and methane, all between like 0.5 and 3 microns, basically. And so we're going to ask ourselves, well, okay, what instruments can detect that? So what if we find an Earth that transits a white dwarf? That would probably be like one of the biggest discoveries of the century, frankly. And we could use MODIS to say, okay, here is, here's an oxygen feature. Here's a CO feature. Here's a methane feature. These all fall within the MODIS window. They also fall within the GMT-NURS window. Interestingly enough, METIS is out here at 3 to 5 microns, where you have CO2 and N2O, and it's not, you can't see it in the plot, but this is also a big window for carbon monoxide. So METIS is actually going to be really good for determining whether a planet is Venus-like. Venus has a lot of carbon monoxide. It's going to be able to, it obviously has a lot of CO2 as well. So this is going to be an instrument that says this planet is Venusian, perhaps it's not habitable. Let's see. So yeah, I just said this. Now I want to talk about a huge, huge problem that we're going to have when ELTs come online, the degeneracy problem. And this is just saying that in our own solar system, we have 4 terrestrial planets, and they all have vastly different atmospheres. Now, if you multiply this by 1 million, you'll get the kind of scale of the problem that we're going to be looking at once we have the capabilities to look at terrestrial planets. So basically, we're going to say, okay, we found this bright Earth-like planet, and maybe it transits a nearby star. But what's that planet atmosphere made of? What are the major components of it? We're just going to have absolutely no idea because the variety is just so great. So we might have 1,000 models to choose from. We might have 1 million models to choose from. How much time is it going to take to cross-correlate all these models against the spectra that we obtain of this planet? Better methods have to be developed. So this is an example of the denoising level that we need to come to. So this is, a nice exoplanet spectrum. Here are some features. Here there are no features. Now, if you look at the even the SPORK caloric removed spectrum, you can't tell where there's features and where there's no features. We need to get to the point where we can actually look at a spectrum and say, okay, we think there is some kind of molecular band here. We think that there's nothing here. This is going to require, for one, extensive computing resources. We're going to have to generate, it can take weeks to generate a single model of a hot Jupiter atmosphere. So when we want to run GCMs of terrestrial planet atmospheres, that's just going to take an obscene amount of computing resources. So hopefully we will have obtained that level of computing resources by the time we get to this point. We're also going to need to not just generate those models, but cross-correlate all these spectra with models. We're going to need to denoise stuff. This might involve machine learning. And finally, I kind of want to think about out-of-the-box statistical methods instead of cross-correlation. We might want to use template matching. We might want to use voice recognition algorithm. And voice recognition algorithms is something I think can actually play a really big role in the future of exoplanet science. Because if you're at home and your kids are running around screaming and maybe there's construction going on, and you say to your Alexa, "Hey Alexa, buy me a refrigerator, play the new Taylor Swift song." Your Alexa has to hear what you're saying, despite the fact that there's noise in the background, and it has to quickly match what you said to a huge library of what you could possibly have said. And so this is very similar to the problem at hand, where we have one noisy signal and we need to quickly match it to a huge library of things it could potentially be. And so I think this will be a really fascinating avenue to explore over the next 10 years. Hopefully we will be able to solve the degeneracy problem before we run into it. So essentially, all this is to say that we're preparing for the era of ELTs with simulation, with preparing for the degeneracy problem. And so ultimately, this is going to tell us not just is a planet inhabited, but hopefully we'll be able to tell, does a planet actually host life? So to kind of bring it all back to the Drake equation, we have the fraction of stars which have planets. That's all seamstress. We have the the number of habitable planets. That is something that we can start to address with today's technology. And the frequency of life appearing on a planet, that's all the ELT regime. So in conclusion, I'm constraining the origins of planet formation, improving our ability to characterize atmospheres, and preparing to identify inhabited worlds. Here's my email, my website, my Twitter especially. Here's all my collaborators, and thank you for listening.
Thank you so much, Kaitlin. That was a really, really great talk. I also so interesting. I haven't heard anyone talk about voice recognition as maybe a potential avenue into improving the signal to noise of other science. So that's really interesting to think about. Does anyone have any questions? You can feel free to raise your hand or post in chat. It looks like Avi has a question. Go ahead, Avi.
Hi, Kaitlin. Great talk. Really interesting across a wide range of stuff. Very cool. I was wondering about this, as you sort of started branching into characterization of temperate terrestrial planets with the ELTs, especially with cross correlation, which, you went into a lot. And I was wondering about the problem of caloric contamination from a Earth-like atmosphere on our own planet, getting in the way of the signal of an Earth-like atmosphere on another planet. And the question of whether that really makes the ELT problem for terrestrials much harder than just sort of scaling down or up in signal to noise on what you would need in that sense. Maybe you could, I don't know, with your experience in caloric removal or, sort of decorrelating this. What do you think about that problem?
That's really super interesting. Nobody's ever asked me about tellurics on another planet. The fact that tellurics are just so strong and so variable on Earth-like planets is really pointing toward the fact that we have to absolutely continue to pursue the absolute best methods of telluric removal, just because our tellurics are in the scale of like 1 on a normalized spectrum, and the tellurics that we might be searching for are going to be on the scale of like 10 to the minus 8. So we're just I think one direction we need to continue to pursue is that we need to find the absolute brightest. We need to find planets around stars that we can see in the night sky. That's what's going to get us the kind of signal and noise which is necessary for us to even dream of separating tellurics from exotellurics, if I might call them that. So that's something that I think CHEOPS is, maybe I said that wrong, but CHEOPS, I think that survey is looking at bright nearby stars for radial velocity signatures of really, really like long period Earth-like planet. Of course, finding an Earth-like planet around a white dwarf would be the holy grail of this kind of study, although that's another interesting question itself. What happened to the planet when the white dwarf went poof? But I really think that the best way to solve that is just by finding Earth-like planets around the absolute brightest stars in the sky. All we can really do is get the kind of signal to noise that just maximize it, and hope that people like me really get that telluric removal as good as it can be. Because you're right. Sorry, go ahead.
Well, what about non-transiting planets discovered by RV around the nearest?
That's that is going to be a big thing, is that many planets do not transit. Fortunately, I do emission spectra. So I already study planets which are not transit, but we don't study them at transit. So really reflection spectroscopy is going to be kind of a big thing, which is going to, that's going to be interesting because there will be some radial velocity separation of the planet, not from its star, but from the Earth's atmosphere. Of course, these planets are also going to be moving much more slowly than a hot Jupiter, which is why the resolution is really important. Yeah, that's a very good point. We're going to have to think about reflection spectroscopy and kind of thinking about what's going to happen when we can't separate the star from the planet with radial velocity separation. But yeah, you're right. There are many challenges to overcome before we get to the point where we can use an ELT to point it at an exo-Earth and say, here's an exo-Earth. Yeah.
Awesome. Does anyone else have any other questions? Well, I do have one, and the answer might end up going past the hour, so everyone's welcome to hop off. And again, thank you so much, Kaitlin, for your talk. But I did want to poke at something you mentioned. If you could talk about phosphine, and really, I wanted to expand it to just other non-standard biosignatures, and what your thoughts are on these moving forward, because I feel like we're going to get more and more papers like this in the future that try to look at new ways to say a planet is habitable or not, or inhabited or not. So I just wanted to hear more of your thoughts on that.
Yeah, so things that are biosignatures, such as phosphine, are typically not the dominant species in an atmosphere. What I think is much stronger is biosignature pairs, because you may have a whole lot of CO2, you may have a whole lot of O2 in an atmosphere. So the O2, CO2, and methane are going to be well, methane can be very weak as well. That's another whole thing. Once you even get your exoplanet atmosphere, what if it's dominated by CO2 and you just can't find anything else in it? Sorry, the cat is chasing something loud around the living room. Hold on a sec. Nope. Okay. I got the cup. Yeah, so that's going to be another problem we're going to have, is that, you know, a planet might have some dominant species, and that dominant species might just totally bury the actual biosignature. Like, I have looked at Venus. I have personally looked for phosphine on Venus in the infrared, and what we found with that, although there are some infrared phosphine features, they are buried in CO2. So that yet another issue that we're going to run into is we're going to need to use these like major biosignatures such as methane, CO2, O2. And we just may not ever be able to detect phosphine on another world just because the signature is so weak. Although it could be potentially less weak in the radio where the original Venus phosphine was made. I have thoughts on that. As a spectroscopist, nobody should ever use an 11th order polynomial to detrend spectra. Do not do it. That was not good. I have many thoughts about the phosphine detection on Venus. I think there is phosphine on Venus. It's not 20 parts per billion. And I wish I had been part of that discovery, because I would have said, hey, that's fringing, that's not a signal. Anyways, yeah, some biosignatures are just going to be so weak in the atmosphere, even if they exist, that they may be buried by other features. So that's really just another difficulty when we look at you know, when we try to start looking at terrestrial planets, is that there's only going to be so many features we can observe, and it's going to be difficult, but you know, I'm up for the challenge.
Yeah, for sure. I mean, it's the problem of our century, but
Yeah,
that was great. Thank you again so much for this talk. It was really interesting. And if no one else has any other questions, then we can break here. But I hope you have a great move and great holidays coming forward.
thank you so much. I have loved being here. I loved talking about ELTs, especially. People always have great questions about the future and always raise new concerns to add to the big list of concerns about ELTs.
Of course.
But yeah,
They're going to be huge. And as the decadal put out there, it's, you know, we may be having many powerful telescopes on the ground in the future. So, all right. Well, thank you everyone so much for coming out, and thank you again, Kaitlin, for the talk, and hope to see you in person soon. Take care, everyone.
bye everyone.